Hello there, and a very warm welcome to Cosmic Whispers. It's so good to have you with us. Wherever you happen to be right now, perhaps settled in for the evening, or just finding a quiet moment in your day, I invite you to pause. Just for a moment. Consider the room you're in, the city outside, the entire world that feels so solid and all-encompassing. It all feels so permanent, so complete. But what if all of this, everything we've ever known, every historical event, every empire risen and fallen, every grain of sand on every beach, is just a single fleeting breath in a story so vast that our minds can barely grasp its opening chapter? What if our reality is just one tiny illuminated speck in an ocean of existence, so profound it borders on the divine? Tonight, let's embark on a journey. Let's not just look at the stars, but try to comprehend the cosmic cities they inhabit. We're about to fly, not just through the void, but through the very fabric of time, to witness the grand, terrifying, and beautiful lives of the 2 trillion galaxies that populate our observable universe. If you're ready to perhaps feel a little smaller, and yet infinitely more connected, let's begin. In the brief time it takes for you to watch this video, light from the most distant galaxy we have ever discovered will streak another 300 million miles closer to us. It's a journey that light has been on for an almost unimaginable stretch of time. It began its voyage when our universe was a mere infant, barely 280 million years old. This was long before the Earth had even begun to coalesce, before our sun ignited, and before our own Milky Way galaxy looked anything like the majestic spiral we know today. We are about to embark on a flight, a grand tour, through every single one of the 2 trillion galaxies that we can, in theory, observe. You will be a silent witness to impossible collisions, cosmic ballets of destruction and creation that span hundreds of millions of years. We will discover galactic ghosts galaxies that, according to our understanding, simply shouldn't exist. We will gaze upon cosmic structures so vast they make our entire Milky Way look like a single insignificant speck of dust. If you feel ready to truly expand your cosmic perspective, perhaps this is a good moment to tap that like button. Prepare yourselves. Our journey begins now. Everything you think you know about the number of galaxies in our universe is most likely wrong. And not just by a little. It's wrong by a staggering factor of 10. Until very recently, in the grand scheme of cosmic discovery, astronomers would have told you with reasonable confidence that our observable universe contained around 200 billion galaxies. That number itself felt impossibly large, a figure that the human mind could write down but never truly internalize. 200 billion islands of light, each with billions or trillions of its own stars. It was already a populated eternity. But then, the James Webb Space Telescope turned its unparalleled infrared eyes towards patches of space that were believed to be dark, silent, and empty. And in doing so, it didn't just revise our estimates, it shattered them completely. The real number, the one we are now grappling with, is closer to 2 trillion galaxies. Let that number settle in your mind. 2 trillion. This means that for every single galaxy we thought existed, 9 more were hiding in the cosmic shadows. They were lurking just beyond our sight, too faint, too ancient, and too distant for our previous generations of telescopes to ever detect. Think about this confirmed fact. In the time it takes you to simply blink your eyes, light from thousands of these newly discovered galaxies crosses another mile of the cosmic void on its long, patient journey toward Earth. Some of that light, some of those ancient photons, have been traveling since long before our solar system ever formed. We are, quite literally, looking at the baby pictures of the universe. And as it turns out, there are far, far more babies than we ever could have imagined. The Hubble Space Telescope, our faithful eye in the sky for decades, gave us the first tantalizing hint of this hidden population. It did so when astronomers made a bold, almost audacious decision. They pointed the telescope at a patch of sky that looked completely, utterly empty. They called it the ultra-deep field. This wasn't a quick snapshot. This image required 800 separate exposures, meticulously collected over 11 long days. Hubble stared and stared and stared into the void. The patch of sky it was observing was impossibly small to near than a single grain of sand held at arm's length. And what it found in that tiny slice of apparent emptiness was staggering. It found 10,000 galaxies. Not 10,000 stars, 10,000 entire worlds. Each a distinct galaxy, some spirals like our own, some chaotic blobs, some ancient red dots. Each one of them containing billions, perhaps hundreds of billions, of stars. All of them crammed into a space that would be completely covered by the period at the end of this sentence if you held it up to the night sky. But here is where the story gets truly mind-bending, and where the new reality from the Webb telescope comes in. That ultra-deep field, with its 10,000 galaxies, represents just 1/13 millionth of the entire sky. If you were to multiply those 10,000 galaxies by 13 million, you would begin to grasp the sheer scale we are dealing with. And yet, even that calculation, which gave us the 200 billion figure, was profoundly conservative. Why? Because Hubble sees the universe primarily in visible light, the same light our eyes can see. The most ancient, distant galaxies have had their light stretched by the very expansion of the universe, a process called redshift. Their light, which may have started as blue or white, has been pulled like a cosmic rubber band over 13 billion years, stretching all the way into the infrared spectrum. Hubble was blind to them. It was like trying to hear a symphony when you can only detect the highest notes. The James Webb Space Telescope, however, was built specifically to see in infrared. It sees the stretched, ancient, and faint light from the universe's dawn. And when it looked at that same empty sky, it found those 9 other galaxies for every one Hubble saw. Galaxies so small and faint, they are like trying to spot a candle flame left on the surface of the moon. Each one of these faint, red smudges represents hundreds of millions, or perhaps even trillions, of stars. Each one represents planets and nebulae and cosmic possibilities. Each one represents entire civilizations that could have risen and fallen billions of years before our planet even formed, civilizations we will, in all likelihood, never know. The mathematics of this new reality becomes almost meaningless. If we take a conservative guess and say that every galaxy contained only 100 billion stars, like our Milky Way, though many are larger, we are looking at 200 sextillion stars in the observable universe alone. That is a 2 followed by 23 zeros. 200 quintillion. This is, famously, more stars than there are grains of sand on every single beach and in every single desert on planet Earth. And remember, this is only what we can observe. This is our bubble of reality, the part of the universe whose light has had time to reach us. The actual universe almost certainly extends far, far beyond our cosmic horizon, possibly containing infinite galaxies, stretching in all directions forever. What we can see, this universe of 2 trillion galaxies, may just be a tiny illuminated bubble in an ocean of space that has no edge at all. But as staggering as these numbers are, they pale in comparison to the violence, the beauty, and the sheer cosmic drama hiding within each and every one of these cosmic islands. Right now, as you sit there, you are hurtling through the void at over 1.3 million miles per hour. And yet, you do not feel a thing. You are not just spinning with the Earth or orbiting our sun. You are being carried along by the entire Milky Way galaxy as it barrels through intergalactic space, itself caught in a gravitational current, pulling it toward an inevitable, distant cosmic collision. We are not alone on this journey. Our galaxy, our home, belongs to a gravitationally bound family that astronomers call the local group. This is our immediate cosmic neighborhood. It's a cluster of more than 54 distinct galaxies, all performing an intricate, slow-motion cosmic dance, bound together by their mutual gravity. The local group spans a truly enormous distance, roughly 10 million light-years across. To try and put that into perspective, if our entire Milky Way galaxy were shrunk down to the size of a single dinner plate, our nearest large neighbor, Andromeda, would be another dinner plate, 250 feet away. The entire local group would be a sprawling city miles across. Within this vast, sprawling neighborhood, 3 galaxies dominate all the others through their sheer mass and gravitational pull. They are the giants, the big 3 of our local family. The largest and most massive is the Andromeda Galaxy, N31. It is a true behemoth, containing over 1 trillion stars and stretching a phenomenal 220,000 light-years from one end to the other. That makes it roughly twice the size of our own galaxy. And as we'll see, it is heading straight toward us at a relentless 68 miles per second. This collision is confirmed. It will happen in approximately 4.5 billion years. But more on that cosmic catastrophe later. Our own Milky Way ranks second in the local group's hierarchy. We are the little brother to Andromeda's Titan, with an estimated 300 billion stars. Though this number is constantly being refined, our galaxy is spread across a disk about 100,000 light-years wide. We are currently positioned about 26,000 light-years from the chaotic supermassive black hole at the galactic center, tucked safely away in what's known as the Orion Arm, one of several spiral structures that give our galaxy its distinctive, beautiful pinwheel shape. The third major player is the Triangulum Galaxy, M33. It is a beautiful spiral galaxy, but significantly smaller, about half the size of the Milky Way, and containing roughly 40 billion stars. While it's dwarfed by its 2 massive neighbors, Triangulum is notable for being a frantic stellar nursery. It has one of the highest rates of star formation in the entire local group, birthing new suns at nearly twice the rate of our own galaxy. But these 3 giants are not alone. They are surrounded by dozens of smaller satellite galaxies, many of which orbit our own Milky Way like cosmic pets, or perhaps more accurately, like moths circling a flame. The largest and most famous of these satellites are the Large and Small Magellanic Clouds, which are visible to the naked eye from the southern hemisphere as 2 fuzzy, ethereal patches of light against the dark. The Large Magellanic Cloud contains about 30 billion stars, while its smaller companion hosts roughly 3 billion. What's fascinating and truly humbling is that this entire local group structure, all 54+ galaxies, is itself just a tiny, insignificant speck within an even larger cosmic architecture. We are located on the absolute outer edge of something called the Laniakea supercluster. The name Laniakea means immense heaven in Hawaiian, and it is our true cosmic address. This supercluster is a colossal collection of roughly 100,000 galaxies, including our own, all loosely connected, spanning an incomprehensible 520 million light-years. And all of them, all 100,000 galaxies, including our local group, are flowing. They are like water in a cosmic river, all streaming toward a mysterious, unseen, and utterly terrifying gravitational anomaly known as the Great Attractor. This cosmic monster, located roughly 250 million light-years away, has the mass of tens of thousands of galaxies. We come and see it clearly, because it is hidden behind the gas and dust of our own Milky Way's disk. But we know it's there. We can feel its pull. It is pulling our entire local group and thousands of other galaxies toward it at over 1.3 million miles per hour. Yet even as we are being drawn inexorably toward this distant massive attractor, the very expansion of space itself, dark energy, that is stretching the fabric of the universe, is simultaneously pushing most other galaxy groups and superclusters away from us. It's like being on a cosmic treadmill. We are in a constant tug-of-war, where some distant destinations get closer, while most others recede from us, eventually to be lost forever over the cosmic horizon. The peaceful, star-dusted appearance of our local group, this cosmic family, masks a violent and brutal reality. It's a truth that has been unfolding for billions of years, hidden in plain sight. The Milky Way is a monster. Our galaxy, our beautiful, serene home, is a cannibal that has been eating its neighbors alive for over 10 billion years. Right now, as you read this, our galaxy is in the slow, agonizing process of violently tearing apart and consuming at least 2 smaller galaxies. The Sagittarius Dwarf Elliptical Galaxy is one such victim. It is being slowly, methodically shredded by our galaxy's immense gravitational field. As it's pulled apart, it leaves behind long, delicate streams of stars that wrap around the Milky Way like cosmic spaghetti, ghostly trails of a murdered galaxy. Meanwhile, the Canis Major Dwarf Galaxy is so thoroughly destroyed, so completely dismembered and absorbed, that astronomers only discovered its remains in 2003. Its stars have been scattered and assimilated into our own galaxy, their original home erased from existence. This process is not gentle. It is not a polite merger. Think of it like a massive, swirling whirlpool in the ocean, encountering a small fishing boat. The dwarf galaxy gets stretched, twisted, and contorted by tidal forces. These forces are so powerful, they are literally ripping individual stars away from their home galaxy's gravitational grip, flinging them into the Milky Way's vast, dark outer halo. Some of these stellar refugees will eventually settle into new stable orbits around our own galactic center, becoming naturalized citizens of the Milky Way. Others will be ejected entirely, cast out into the lonely dark void between galaxies. The evidence for this ongoing galactic cannibalism is written in the stars themselves. Astronomers can identify which stars originally belonged to these destroyed galaxies by studying their chemical compositions and orbital patterns. It's a form of cosmic forensics. Stars from the Sagittarius Dwarf, for example, have a distinctly different chemical fingerprint, a different mix of heavy elements compared to stars that were born and bred in the Milky Way. It's like finding a different DNA signature, allowing scientists to solve celestial crimes that happened billions of years ago. But the Sagittarius Dwarf, our current meal, won't go down without a fight. In its death throes, it is triggering waves of creation. Its disruption is sending gravitational shockwaves through our own galaxy's spiral arms. As the dwarf galaxy's gas clouds collide with the material in the Milky Way's disk, they compress and heat up, creating vast new stellar nurseries where new stars are born at an accelerated rate. In a twisted, beautiful, and cosmic way, the death of this one small galaxy is feeding the birth of countless new stars in our own. And the large and small Magellanic Clouds, those beautiful fuzzy smudges in the southern sky, they are next on the menu. For a long time, we thought they were in stable orbits, permanent companions to our Milky Way. We now know that is not the case. Astronomers have confirmed that both Magellanic Clouds are on a collision course. They are not in a stable orbit. They are spiraling inward. They are expected to be fully consumed within the next 2.4 billion years. When the large Magellanic Cloud, a galaxy with 30 billion stars, finally merges with our Milky Way, the event will be spectacular. The collision will trigger massive, galaxy-wide bursts of star formation, lighting up our night sky with brilliant nebulae. It will also potentially do something terrifying. It will wake up the supermassive black hole at our galaxy's center. The sudden influx of gas and dust from the doomed galaxy could provide a feast for Sagittarius A*, turning it into a brilliant, blinding quasar that could outshine our entire galaxy cluster. This galactic cannibalism isn't unique to us. It's the law of the cosmic jungle. The Andromeda Galaxy, our larger neighbor, has been even more aggressive in consuming its neighbors. Astronomers have identified the faint, ghostly remains of at least 10 different dwarf galaxies in Andromeda's outer regions, their stars stretched into massive, faint streams. The process follows a predictable, brutal pattern throughout the universe. Larger galaxies grow by consuming smaller ones, which in turn had previously consumed even smaller systems. It is a cosmic food chain, and it has been operating since the very first galaxies formed over 13 billion years ago. But all of this local cannibalism, this snacking on dwarf galaxies, is merely the appetizer. The main course is still to come. In 4.5 billion years, the night sky will be on fire. The Andromeda Galaxy, our nearest large neighbor and our sister in the local group, is racing toward us at 68 miles per second. That might not sound incredibly fast compared to the speed of light, but at cosmic scales, it is a relentless, unstoppable march. It is like two titans, each a trillion times more massive than a human, marching toward an inevitable duel. The collision is inevitable. It is confirmed. And it will completely reshape both galaxies in the most violent and spectacular cosmic event our region of space has ever experienced. The Hubble Space Telescope settled this question definitively in 2012. For decades, astronomers knew Andromeda was approaching us, thanks to its blue shifted light, but they couldn't determine its sideways motion. Was it going to be a direct hit, a glancing blow, or a near miss? Hubble's incredibly precise measurements, taken over several years, revealed the terrifying truth. Andromeda is not going to miss. It is aimed directly at the Milky Way's heart. Now, when two galaxies collide, it is not like two solid objects smashing together. It's important to remember that galaxies are, by volume, almost entirely empty space. The average distance between stars is vast. Our nearest stellar neighbor, Proxima Centauri, is 25 trillion miles away. So, the chance of any two individual stars actually hitting each other during this merger is essentially zero. Instead, what happens is far more dramatic, chaotic, and is governed entirely by gravity. The collision will unfold over hundreds of millions of years. A slow-motion catastrophe. It will begin with the outer edges of both galaxies, their vast, thin disks of gas, and stars starting to warp and stretch as they feel each other's immense gravitational pull. Massive tidal forces will sling entire star systems completely out of their home galaxies, ejecting them into the dark, intergalactic void. Some of these ejected stars will carry their planets with them, creating countless orphan solar systems doomed to drift forever through the endless darkness. As the two galactic centers draw closer, their supermassive black holes will begin a deadly and intricate spiral dance. The Milky Way's central black hole, Sagittarius A*, contains the mass of about 4 million suns. Andromeda's is significantly larger, a monster at roughly 100 million solar masses. When these two monsters finally merge, they will unleash one of the most powerful events in the universe. The creation of gravitational waves so powerful, they will ripple through the very fabric of space-time itself, detectable by advanced civilizations, if they exist, billions of light years away. This merger will also trigger the most spectacular fireworks show in cosmic history. Trillions of tons of gas clouds from both galaxies will collide, compress, and ignite. This will set off massive, uncontrolled bursts of star formation, lighting up the combined system like a cosmic Christmas tree. New stars will be born at a rate 10 times faster than what we see in either galaxy today. What about Earth? What is our fate during this collision? Computer simulations have modeled this event thousands of times, and the answer depends on a degree of cosmic luck. The simulations suggest there's roughly a 50% chance that our entire solar system will be gravitationally ejected from its current peaceful orbit and flung 3 times farther from the new galactic center than we are now. There is also a more terrifying 12% chance that we will be ejected from the merged galaxy entirely, sent wandering as a rogue solar system through the cold darkness between galaxy clusters. But here's the truly mind-bending part. If humanity, or whatever we've become, still exists when this collision begins, We will have front row seats to watch it unfold over millions of generations. The night sky will gradually fill with new stars as Andromeda grows larger and brighter. Eventually, it will dominate the entire sky, a spectacular, terrifying spiral of fire stretching from horizon to horizon. The final product of this cosmic catastrophe will be a new, single, giant elliptical galaxy. The elegant spirals of both the Milky Way and Andromeda will be gone, their structures scrambled into a massive, chaotic blob of stars. Astronomers have already given this future galaxy a nickname, Milkomeda. It will be roughly 10 times more massive than either original galaxy and will rank among the largest and oldest-looking galaxies in our local supercluster. But even this ultimate universe-altering collision pales in comparison to galaxies that have already died in ways that well, in ways that shouldn't be possible. There are galaxies out there that have been dead for billions of years, and scientists have absolutely no idea how they died. Meet Max 2129-1. From a distance, it looks like a perfectly normal, healthy spiral galaxy. In fact, it's a behemoth, spinning twice as fast as our Milky Way and containing several times more mass. But when astronomers looked closer, they discovered something that breaks every single model of galaxy evolution we have. This galaxy stopped forming new stars over 10 billion years ago. It is a cosmic zombie, a walking corpse that challenges everything we thought we knew about how galaxies live and die. Dead galaxies, or quenched galaxies as astronomers call them, are systems where star formation has completely and totally shut down. In a normal, living galaxy like ours, massive clouds of cold gas and dust are constantly collapsing under their own gravity to birth new generations of stars. This process should continue for trillions of years, until the universe itself expands so much that galaxies can no longer hold on to their precious gas supplies. But Max 21291 defied this natural order. Somehow, when the universe was less than a quarter of its current age, just a toddler, this massive galaxy either exhausted or violently expelled all of its star-forming material. The problem is, according to our best models, this should be impossible for a galaxy of its size and type. Small, lightweight dwarf galaxies can be quenched relatively easily. A nearby supernova explosion, or the gravitational influence of a larger galaxy, can strip away their gas supplies, effectively sterilizing them. But massive spiral galaxies, like Max 2129-1, are supposed to be robust. They should have more than enough gravitational pull to hold onto their gas, no matter what cosmic violence occurs around them. They have what astronomers call gravitational authority. The discovery gets even stranger when you examine the galaxy's internal structure. Most of the other dead galaxies that astronomers have found are elliptical in shape. They look like giant, cosmic footballs, with stars distributed randomly. This shape makes sense because we believe they form when two spiral galaxies, like ours, and Andromedas collide and merge, scrambling their organized, beautiful structures into a random, chaotic blob. But Max 2129-1, it maintained its spiral structure even as it died. The galaxy's stars are still arranged in elegant, curved arms, radiating out from a central bulge, exactly like a living spiral galaxy. It's like finding a perfectly preserved mummy that looks completely alive from the outside, but contains no spark of life, no breath, no warmth within. Even more puzzling, a spectroscopic analysis at Cosmic Forensics we talked about reveals that the stars in this dead galaxy didn't form through the violent mergers that astronomers expected. Instead, they appear to have formed early in the galaxy's history through normal, peaceful star formation processes. And then something catastrophic happened. Something shut down all star formation, almost instantly on a cosmic time scale. Several theories have been proposed to explain this profound mystery, but none of them are fully satisfactory. One possibility is that the galaxy's central supermassive black hole went through an extremely active quasar phase, generating powerful jets and radiation that heated up all the surrounding gas to the point where it could no longer cool and collapse into stars. Another theory suggests that the galaxy experienced a series of massive, coordinated supernova explosions that collectively acted like a galactic wind, blowing away its entire gas supply. But the most disturbing possibility, the one that keeps cosmologists up at night, is that we are missing something fundamental about how galaxies evolve. Max 2129-1 might represent a completely unknown process, a fast-acting galactic disease that can kill even the largest, most robust galaxies without warning. And this dead galaxy isn't alone. Astronomers have now identified dozens of similar systems, all scattered throughout the distant universe. All of them are massive spiral galaxies. All of them somehow died billions of years before they should have. Each new discovery adds another piece to a cosmic puzzle that, for now, seems to be growing more mysterious rather than clearer. From a galaxy that died a quiet, mysterious death, we now turn to one that is being violently murdered in full view of the universe. Some galaxies are being torn apart so brutally, so spectacularly, that they look like magnificent jellyfish swimming through a dark cosmic sea. Located 220 million light-years away, in the constellation Triangulum Australe, galaxy ESO 137001 is caught in the very act of being destroyed. The images are breathtaking. The galaxy appears to be swimming through space, trailing long, beautiful, ethereal tentacles of gas and stars behind it. But this isn't a peaceful swim through an empty void. This galaxy is drowning. The destruction is caused by a process called ram pressure stripping. It is one of the most violent and visually stunning ways a galaxy can die. To understand it, imagine you are driving a convertible car at highway speeds through a torrential downpour. The wind doesn't just itch you wet. The sheer force of the air, the ram pressure, strips the rain right off your windshield and flings it backward in long streams. Now, scale that up to cosmic proportions. The galaxy ESO 137001 is not in a quiet neighborhood like our local group. It is falling at over 4 million miles per hour into the heart of a massive galaxy cluster. The space between galaxies in this cluster isn't empty. It's filled with an extremely thin but incredibly hot gas, a soup of plasma, heated to temperatures of over 100 million degrees Fahrenheit. This intergalactic medium is so thin that it would count as a perfect vacuum by any Earth-based standard. But when you are moving through it at 4 million miles per hour, it becomes like hitting a brick wall. The ram pressure from this hot, invisible medium is literally stripping away ESO 1371's own cooler gas supplies. The galaxy's outer layers, its precious star-forming fuel, are being peeled off like the skin of an onion, creating those spectacular trails, or tentacles, that stretch for over 200,000 light-years behind the galaxy. These trails contain enough material to form billions of new stars. But instead of fueling the galaxy's growth, this precious gas is being scattered into the void, lost forever. What makes the imagery even more striking is that the stripped gas doesn't just disappear. As it gets torn away from the galaxy, it forms these intricate, delicate structures that truly do resemble the tentacles of a jellyfish. And these tentacles are illuminated. They are lit up by the brilliant ultraviolet radiation from young, hot, blue stars that are still managing to form within the stripped material. It's a final, beautiful burst of life, creating an eerie blue glow against the blackness of space. This process is irreversible. It is ultimately fatal. Once a galaxy loses its gas supplies, it can no longer form new stars. The existing stars will continue to shine for billions of years, but gradually, the galaxy will fade. Its most massive stars will burn out and explode as supernova. Eventually, only the dim, cool red dwarf stars will remain, turning the once vibrant galaxy into a cosmic ghost. Astronomers have now identified dozens of these jellyfish galaxies throughout nearby galaxy clusters. Each one tells the same tragic, beautiful story. They are all caught in different stages of the stripping process, from galaxies just beginning to lose their outer gas layers, to systems so thoroughly destroyed that only faint tentacles remain of what was once a thriving stellar metropolis. The Hubble Space Telescope has captured some of the most dramatic images of this destruction in action. In cluster after cluster, galaxies appear to be racing away from their own scattered remains, leaving trails of star formation in their wake like cosmic contrails. The most haunting aspect of jellyfish galaxies is what they represent: cosmic beauty born from cosmic violence. These systems are among the most photogenic objects in the universe. Yet each one represents the death throes of a cosmic civilization, a home that might have harbored billions of worlds. Even the violent, beautiful death of a jellyfish galaxy seems to follow a certain logic. But what about a galaxy that challenges our most basic understanding of reality itself? There is a galaxy out there that, by all rights, should not exist. Its very presence is breaking our understanding of how the universe works. The galaxy is named NGC 1277. It was found to contain virtually no dark matter. This is like finding a human skeleton ... without any bones. Let's back up. What is dark matter? It is the invisible, mysterious something that makes up roughly 85% of all matter in the universe. It provides the invisible scaffolding, the cosmic web that allows galaxies to form and maintain their structure. Without it, the gravity of the normal matter, the stars, gas, and dust wouldn't be strong enough to hold a galaxy together. Galaxies should either fly apart or, more likely, never have formed in the first place. Dark matter is the invisible glue that holds galaxy clusters together. It's the reason why the outer arms of spiral galaxies, like ours, spin as fast as they do without flying off into space. It is, quite simply, one of the fundamental pillars of modern cosmology. We can't see it. We can't touch it. We have no idea what it's made of. But we know it's there, because we can see its gravitational effects everywhere we look in the universe. And then, there is NGC 1277. This discovery sent profound shockwaves through the astronomical community when it was announced. NGC 1277 is what's known as a relic galaxy. This means it formed very early in cosmic history and has remained largely unchanged for billions of years. It's several times more massive than our Milky Way, but all its stars are packed into a much smaller volume, making it incredibly dense. But despite containing hundreds of billions of stars, meticulous measurements show it has virtually no dark matter halo surrounding it. It seems to be held together by nothing but the gravity of its own visible stars, which shouldn't be possible. The initial discovery was so controversial, so reality-breaking, that it was assumed to be an error. Several independent teams of scientists double-checked the measurements. They looked for errors in the data. They proposed alternative explanations. Maybe the galaxy was actually closer than originally thought, which would change the mass calculations. Maybe it had dark matter once, but it had been somehow stripped away by interactions with neighboring galaxies in the massive Perseus cluster where it resides. But follow-up observations with multiple, powerful telescopes all confirmed the impossible. NGC 1277 does, indeed, appear to be a massive galaxy with little to no dark matter. The finding was so significant that it has forced scientists to seriously reconsider some of their most basic assumptions about how the universe works. One proposed explanation is that NGC 1277 formed through an extremely rare, specialized process, where the normal, baryonic matter was somehow separated from the dark matter during the galaxy's birth. Another, more likely, possibility is the one mentioned before, that the galaxy's dark matter was stripped away. The Perseus cluster's enormous gravitational field might have been able to pull away the galaxy's vast, diffuse dark matter halo, while leaving the more tightly bound normal matter, the stars, behind. But the most disturbing possibility, the one that makes this a true cosmic mystery, is that our entire understanding of dark matter is fundamentally flawed. Maybe what we interpret as dark matter isn't a thing at all, but is actually a misunderstanding, a sign that we need to modify the laws of gravity under certain conditions. If that's true, then NGC 1277 might be showing us what galaxies look like when this modified gravity effect is somehow turned off. This single object has opened up a Pandora's box of questions. Are there other galaxies like this hiding in the universe? Could entire regions of space exist where dark matter is absent? And what does this mean for our understanding of how any structure formed in the early universe? What is certain is that NGC 1277 represents a profound cosmic anomaly. It is a galaxy that, by all our rules, should not be. And its very existence challenges everything we thought we knew about reality. But if a galaxy without its invisible scaffolding seems impossible, what about a galaxy from the dawn of time, where the fuel for the fire shines brighter than the fire itself? There's a galaxy in the early universe, GSND 9422, where the gas clouds are shining brighter than all of its stars combined. Scientists who found it are calling it a totally new phenomenon. This galaxy exists from a time when the universe was only 1 billion years old, less than 10% of its current age. It is a relic from the cosmic dawn, when the very first stars and galaxies were just beginning to flicker on. When astronomers first looked at its spectrum of light, they found something that had never been seen before. They found the signature of superheated gas that was outshining the galaxy's entire stellar population. In all normal galaxies, stars are by far the brightest objects. They are nuclear fusion reactors, converting matter into energy at temperatures of millions of degrees. They pump out enormous amounts of light across all wavelengths. The gas between the stars, while critically important for forming new stars, typically just glows faintly in specific narrow wavelengths, illuminated by the stars themselves. But in GSND 9422, this relationship is inverted. The gas is the main event. The stars are just a sideshow. What could possibly cause this? What could heat up an entire galaxy's worth of gas to such extreme temperatures that it outshines its own stars? The truth is, we don't know. Is it a colossal, hidden supermassive black hole, a primordial quasar that is pouring unfathomable amounts of energy into its surroundings, heating the gas from within? Is it the hypermerger of dozens of smaller, primordial galaxies all crashing together at once, with the resulting shock waves heating the gas to extreme temperatures? Or is it something even more exotic, a process unique to the early universe, a form of matter or energy that we haven't even theorized about, that only existed when the cosmos was young? This single, strange galaxy is a puzzle box from the dawn of time. It reminds us that no matter how much we learn, no matter how powerful our telescopes become, the universe will always hold more mysteries. It is a universe not just of 2 trillion galaxies, but of 2 trillion stories of birth, of violent life, of strange death, and of impossible realities. We were just discussing that profound mystery, the galaxy GSND 9422, a puzzle box from the dawn of time. The mystery only deepens when we look at the astonishing numbers involved. In this galaxy, the normal relationship between stars and the gas that surrounds them has been turned completely upside down. Its vast clouds of interstellar gas are being superheated to over 140,000 Fahrenheit. That's roughly 78,000 Celsius. This is a temperature nearly twice as hot as the surface of typical massive stars. At these extreme temperatures, the gas itself becomes incandescent, blazing with such energetic light that it outshines the galaxy's entire population of stars. This discovery was made possible by the James Webb Space Telescope's powerful infrared spectrograph. This instrument acts as a cosmic prism, catching the faint, ancient light from this galaxy and breaking it down into its component wavelengths, revealing its chemical fingerprint. When the lead researcher, Alex Cameron, first examined the data, his reaction was one of pure, unfiltered scientific shock. His simple, immediate assessment, "That's weird." It was, in fact, exactly the kind of totally new phenomenon that the Webb telescope was designed to find in the deep, early universe. The spectrum, the data from that light, showed the unmistakable signatures of highly ionized gas. This means the atoms in these vast, galaxy-spanning clouds have been violently stripped of most of their electrons. This ionization process requires a colossal, overwhelming input of high-energy radiation far more than all the observed stars in that galaxy should be able to provide. It truly is, as we've hinted, like finding a massive pot of water boiling furiously. But when you look beneath it, you find only a single tiny candle flame. The energy output simply doesn't match the energy source. Working with theorist Harley Katz, the team ran sophisticated computer models to try and answer the one burning question: what could possibly create such extreme, unexplained conditions? Their conclusion is as fascinating as the discovery itself. It suggests that GSND G9422 contains a different kind of star. Not the stars we are familiar with, but primordial monsters, stars that are far hotter and more massive than anything that exists in our local universe today. These primordial behemoths might have reached surface temperatures of over 140 degrees Fahrenheit, making them incredibly, almost absurdly, efficient at pumping out the exact kind of high-energy ultraviolet radiation needed to superheat the entire galaxy's gas supply. As you might guess, the implications of this discovery extend far beyond just one weird galaxy. This strange gas outshining phenomenon might represent a long-sought-after missing link in our understanding of how the universe itself evolved from its dark, opaque beginnings into the star-filled cosmos we see today. During the first few 100 million years after the Big Bang, the universe was filled with a thick neutral hydrogen gas. It was a dark age, where this primordial fog blocked most light from traveling very far. Something had to burn off that fog. Something had to ionize all of that hydrogen to make the universe transparent, an event astronomers call the epoch of reionization. It has long been suspected that the very first generation of stars was responsible for this. But there's a persistent problem with that theory. Regular stars, even the massive ones we know today, don't seem capable of producing enough of the right kind of ultraviolet radiation to get the job done. Our models of reionization always come up a bit short. But galaxies like GSND G9422, with their superheated gas and their hypothetical primordial monster stars, might be showing us exactly how it happened. These stars, theorized to be hundreds of times more massive than our Sun, would have lived incredibly brief, extraordinarily violent lives, exploding and seeding the universe with its very first heavy elements. GSND G9422 provides the first observational evidence that such extreme, hyper-efficient stellar populations might have actually existed. And yet, as profoundly strange as this ancient gaslit galaxy is, it seems almost normal when compared to the other impossible systems that have somehow managed to assemble themselves, fully formed, in the cradle of the cosmos. The James Webb Space Telescope, in its short time observing the heavens, has found galaxies that are so massive and formed so impossibly early that they are quite literally breaking our models of how the universe is supposed to work. Meet the red monsters. This is the nickname given to a set of 3 galaxies that astronomers have confirmed contain as much mass as our entire Milky Way galaxy. The problem? They existed when the universe was less than 1 billion years old. This simply should not be possible. It's like finding a fully grown 40-year-old adult in a photograph of a preschool class. It violates our entire understanding of growth and development. According to our best, most refined theories of galaxy formation, a process called hierarchical assembly. These massive systems should not have had enough time to assemble. The red monsters get their name from their distinctive appearance in Webb's infrared images. They glow with a deep, murky red color. This color is a crucial clue, and it points to a second simultaneous mystery. The red glow indicates that these galaxies are packed, absolutely choked, with dust. This dust, made of complex particles, absorbs the blue and ultraviolet light from their stars and re-emits it as a long-wavelength infrared radiation that Webb is so adept at detecting. Why is this a mystery? Because dust grains, the complex, sooty particles of carbon, silicon, and oxygen, are not primordial. They are not created in the Big Bang. They must be forged in the nuclear furnaces of stars, and then expelled when those stars die in supernova explosions. This is a process that is supposed to take multiple generations of stars, unfolding over billions of years. So the question is twofold and confounding. How did these infant galaxies, already impossibly large for their age, also manage to accumulate so much complex, processed dust so very quickly? Galaxy formation in the early universe, as we've understood it, was supposed to be a slow, patient, and gradual process. According to the Standard Model, it all starts with small, invisible clumps of dark matter. These clumps slowly grow larger over eons, their gravity pulling in more matter. Eventually, they become massive enough to trap the primordial hydrogen gas, which then begins to cool, collapse, and form the first stars. This is a bottom-up process. Small things form first, then they merge to make bigger things. This process, we believed, should take billions of years to create a galaxy as large, massive, and mature as our Milky Way. The red monsters, however, appear to have compressed this entire evolutionary sequence, from cosmic infancy to galactic metropolis, into less than 1 billion years. They are also forming new stars at a frantic, almost desperate pace, nearly twice the rate of similar mass galaxies in the universe today. This suggests that the entire process of star formation in the early universe was far more efficient than our models have ever predicted. The discovery came from the FRESCO survey, which uses Webb's near-infrared camera combined with a GRISM spectrograph to precisely measure the distances and masses of these early galaxies. Out of the hundreds of galaxies this survey studied, these 3 red monsters stood out as clear, undeniable outliers. They were cosmic impossibilities that demanded an explanation. What makes this finding even more puzzling is how they are forming stars. These massive galaxies seem to be converting a much higher percentage of their available gas into stars than we thought was physically possible. In all normal galaxy formation, there's a natural feedback mechanism. As massive stars are born, their intense radiation and the subsequent powerful supernova explosions push back. They heat up and blow away most of the surrounding gas, the very fuel that could have formed other stars. This feedback process acts like a cosmic thermostat, preventing a galaxy from becoming too massive, too quickly. But somehow, the red monsters overcame this natural limitation. They managed to hold on to their precious gas supplies and convert them into stars with an unprecedented, ferocious efficiency. It's like finding a factory that is operating at 200% capacity, 24/7, with no waste, no breakdowns, and no safety protocols, all of the things that should have shut it down. The implications are, of course, profound. They suggest that the cosmic environment 1 billion years after the Big Bang was fundamentally different from what we see today. Maybe the intergalactic medium was far denser, making it easier for galaxies to accrete new material. Maybe that crucial supernova feedback, which regulates star birth today, was, for some reason, much less effective at early times. Or ... maybe our entire understanding of dark matter and the very physics of galaxy formation is missing crucial pieces. The red monsters might be telling us that there are physical processes that were operating in the early universe that we haven't even discovered yet. Each of these red monsters contains roughly 300 billion stars, a mass comparable to our own Milky Way. But all that mass is packed into much smaller, more compact volumes, making them incredibly dense. A discovery of the red monsters represents what researchers are now calling the too many, too massive problem. It's not just that these individual galaxies grew larger than expected. The real problem, the one that is keeping cosmologists up at night, is that there are too many of them. Our models predicted that such massive early galaxies should be extraordinarily rare, a single shocking needle in a cosmic haystack. Yet, Webb is finding them almost everywhere it looks. This abundance of early massive galaxies is forcing astronomers to go back to the drawing board, to reconsider some of their most basic, fundamental assumptions about cosmic evolution. But even these cosmic impossibilities, these red monsters, pale in comparison to the most distant object we have ever set our eyes upon. We are about to look at a true cosmic time machine, a single galaxy that takes us back to when the universe was barely out of its infancy. We are now looking at the most distant object ever discovered by humanity. It is a galaxy that existed when the universe was only 280 million years old. Not billion, million. The galaxy, designated MOMZ14 in the survey, represents the ultimate time machine. It is showing us the conditions of our cosmos when it was barely 2% of its current age. The light reaching our telescopes today from this cosmic infant began its journey over 13.5 billion years ago. It has been traveling across the expanding void for nearly the entire history of time and space. MOMZ14 earned its nickname as the mother of all early galaxies because it completely shattered the previous distance record, pushing it back by a full 20 million years. That may not sound like much to us, but in the context of the early universe, 20 million years is a significant fraction of the total time that had elapsed since the Big Bang. Finding this galaxy required pushing the James Webb Space Telescope to its absolute existential limits. Even with Webb's unprecedented infrared sensitivity, MOMZ14 appears as just a few faint pixels of reddish light swimming against the noise of the cosmic background. But those few pixels, contain information that has traveled farther through space and time than any signal humanity has ever detected. Its extreme distance means we are seeing a MOMZ14 at a redshift of Z equals 14.44. Redshift is the critical measurement of how much the expansion of the universe has stretched the wavelengths of light during its long journey to us. A redshift of 14.44 means the galaxy's light has been stretched by a factor of over 15. Its visible light, its ultraviolet light, all of it has been pulled, like a cosmic rubber band, into the deep infrared wavelengths where only Webb can detect them. What makes MOMZ14 even more remarkable is that it's not just distant. It is also surprisingly massive and bright for such an early galaxy. The system already contains several 100 million times the mass of our Sun, all packed into a region spanning roughly 1,600 light-years across. That is incredibly compact, suggesting that star formation in the primordial universe was far more concentrated and intense than we see today. The galaxy appears to be in the midst of a furious burst of star formation, creating new suns at a rate that would build the equivalent of our entire solar system every few years. The discovery of MOMZ14 came through the Mirage or Miracle survey. It's a perfect name. The survey uses Webb as spectrograph to confirm whether these candidate early galaxies are really as distant as they appear, or if they are just mirages, nearby imposters that are just reddened by dust. MOMZ14 proved to be a genuine miracle. The spectroscopic analysis confirmed its extreme distance. But it also revealed something that should be impossible. The galaxy contains surprisingly heavy elements. The light signature, that cosmic fingerprint, shows clear traces of oxygen and other metals, the term astronomers use for any element heavier than hydrogen and helium. This is the real shock. Oxygen is not made in the Big Bang. It is forged deep in the nuclear hearts of massive stars, which then have to live their entire lives and explode as supernova to scatter that oxygen into space. Only then can it be incorporated into the next generation of stars. The presence of oxygen in a galaxy at 280 million years implies that multiple generations of massive stars had already lived, died, and recycled their elements by this impossibly early time. It suggests that the very first star formation must have begun even earlier than we thought possible, perhaps just 100 or 150 million years after the Big Bang. Perhaps the most mind-boggling realization is that we are seeing MOMZ-14 as it appeared when the universe was just emerging from its cosmic dark ages. This was an era when most of space was still filled with that neutral, light-blocking hydrogen fog. The galaxy we are observing existed at the very beginning of cosmic reionization, one of the first brilliant pinpricks of light that began the process of clearing away the primordial fog and lighting up the universe. MOMZ-14 is just one member, albeit a record-breaking one, of a growing population of early galaxies that are completely rewriting the story of the cosmic dawn. The epoch between roughly 200 million and 1 billion years after the Big Bang represents the single most dramatic transformation in the history of the universe. It is this era, aptly named Cosmic Dawn, that witnessed the birth of the very first stars, the formation of the first galaxies, and the complete restructuring of all the matter in the universe. It was the grand transition from a dark, neutral, and featureless fog into the transparent, brilliant, star-filled cosmos we see today. Before Cosmic Dawn, the universe was, quite literally, dark. No stars existed to produce light. The afterglow of the Big Bang, the cosmic microwave background, had cooled and faded far below the wavelengths of visible light. Space was filled with nothing but a cold, invisible neutral hydrogen gas and the mysterious invisible scaffolding of dark matter. If you could somehow travel back to this time, 400 million years after the Big Bang, you would see ... nothing. You would not be able to see your hand in front of your face. It was a universe of absolute, total blackness. But hidden within this darkness, gravity was slowly, patiently, relentlessly at work. The tiny, quantum-scale variations in the density of dark matter, imprinted during the first fraction of a second after the Big Bang, had been growing larger over millions of years. These halos of dark matter eventually became massive enough to gravitationally trap the surrounding hydrogen gas, creating the dense pockets of raw material for the first stars. The very first generation of stars, known as population 3 stars, were unlike anything that exists in the universe today. With no heavy elements available, because none had been created, yet these primordial giants formed from pure hydrogen and helium. Computer models suggest they were monsters, true behemoths containing hundreds of times more mass than our sun. They would have burned at impossibly hot temperatures, blazing with a fierce blue-white light. These stellar titans lived fast and died young. They blazed for just a few million years before exploding as cataclysmic hypernovae. Their deaths were, perhaps, the most important event in cosmic history. They seeded the surrounding space with the first heavy elements, the first carbon, the first oxygen, the first iron. This pollution allowed the second generation of stars to form with more diverse chemistry. It was this second generation that began assembling into the first true galaxies, the very ones Webb is now finding. The James Webb Space Telescope is giving us our first direct, tantalizing glimpses of this cosmic dawn by detecting galaxies from this crucial epoch. Each discovery is a time-traveling fossil, preserving the conditions that existed over 13 billion years ago. What's emerging from Webb's observations is a picture of cosmic dawn that is far more violent, chaotic, and rapid than astronomers ever expected. The early galaxies, as we've seen, are more massive, more active, and more numerous than our models predicted. The star formation rates in these systems are off the charts. It seems the first billion years of cosmic history were characterized by an incredibly rapid and efficient assembly of galaxies. The universe's transition from total darkness to a cosmos ablaze with light happened faster and far more dramatically than anyone ever imagined. But these individual early galaxies, forming in the dawn of time, were just the beginning of a new kind of cosmic violence. A violence that would come to reshape entire regions of space and continues to this day. Let's leave the dawn of time and travel much closer to home, to a mere 68 million light-years away in the constellation Corvus. Here, we can see two galaxies that have been locked in a cosmic death spiral for over 600 million years. We are watching right now the final act of their violent, beautiful, and creative ballet. They are known as the antennae galaxies, officially designated NGC 4038 and NGC 4039. They earned their nickname from the two spectacular tidal tails that stretch out from their distorted cores, like the long, graceful antennae of some cosmic insect. But these are not gentle appendages. They are vast, flowing streams of stars, gas, and dark matter being violently torn from their parent galaxies by gravitational forces that dwarf anything we can possibly imagine. This collision, this celestial dance of destruction and creation, began around 600 million years ago. At that time, both galaxies were probably beautiful, well-ordered spiral systems, much like our own Milky Way or Andromeda. But as they drew closer together, their mutual gravity began to pull and twist. Their elegant, flat spiral shapes were hopelessly distorted, and billions of stars and vast clouds of gas were pulled out into these long, streaming filaments that now stretch over 200,000 light-years into space. The violence of this encounter is difficult to comprehend. Each galaxy contains hundreds of billions of stars, and all of them are being gradually accelerated, decelerated, and flung around by chaotic gravitational forces millions of times, stronger than anything our solar system ever experiences. As we've discussed before, the stars themselves won't collide. The space between them is too vast, but their orbits will be scrambled beyond recognition. Some stars are being ejected entirely from both galaxies, shot out into the cold intergalactic void, destined to wander alone through the darkness for billions of years. But the most spectacular part of this cosmic collision is not the destruction, but the creation it has triggered. When the vast clouds of gas and dust from the two galaxies slam into each other at high speed, they compress and heat up, creating the ideal conditions for a massive, uncontrolled burst of star formation. The antennae system is currently giving birth to new stars at a rate roughly 10 times higher than what we see in a normal, quiet galaxy like our own. These stellar nurseries are visible as brilliant blue and pink regions scattered throughout the chaotic collision zone. The bright blue areas mark massive clusters of incredibly hot, young stars that are pumping out enormous amounts of ultraviolet radiation. The glowing pink regions show where the ultraviolet light is hitting the surrounding hydrogen gas clouds, causing them to glow like cosmic neon signs. The Hubble Space Telescope has revealed that the antennae collision is creating some of the most massive superstar clusters ever observed. These are dense, glittering metropolises, containing millions of stars packed into regions just a few dozen light-years across. Have you ever wondered what that would look like? If our Earth were located near one of these superclusters, our night sky wouldn't have a few thousand faint stars. It would be filled, from horizon to horizon, with thousands of stars brighter than the planet Venus. It would be a sky of perpetual, brilliant twilight, with no true darkness. Computer simulations, our crystal balls for the cosmos, show that the antennae galaxies are still approaching their moment of maximum violence. Over the next few 100 million years, their two galactic cores, each with its own supermassive black hole, will spiral closer and closer together. This will trigger even more intense bursts of star formation, until they finally merge in a cataclysmic event that will send those powerful gravitational waves rippling across the universe. The final product of this collision will be a single, massive, and somewhat boring giant elliptical galaxy. The elegant spirals will be gone, their structures scrambled into a randomized blob of older, redder stars. Most of the gas that currently fuels the starburst will either be converted into new stars or blown away, leaving behind a relatively quiet red and dead system. This transformation from two spirals into one elliptical is one of the fundamental processes that has shaped galaxy evolution throughout cosmic history. The antennae galaxies represent this process caught in the act, allowing astronomers to study exactly how these galactic mergers unfold. And in a way, this collision serves as a chilling, or perhaps thrilling, preview of our own future. It is a glimpse of what will happen when our own Milky Way merges with the Andromeda Galaxy in 4.5 billion years. The physics will be essentially identical, though our merger will be even more massive and spectacular. But individual head-on galaxy collisions, like the antennae, are just small-scale versions of a much larger, more systemic, and crueler cosmic violence. This violence plays out every single day, over eons in the vast, dense, ancient cities of the universe, the great galaxy clusters. In the richest galaxy clusters, smaller galaxies are being systematically tortured, starved, and destroyed by their more massive neighbors. It's a process that astronomers, with a fitting touch of dark humor, call galactic harassment. Let's travel to the Coma Cluster, located 320 million light-years away. This is a true cosmic metropolis, a megacity of galaxies. It contains over 1,000 confirmed galaxies, packed into a region roughly 20 million light-years across. While that might sound spacious at cosmic scales, this represents an incredibly dense concentration of massive objects. They are all moving at tremendous speeds, swirling around a shared deep gravitational well. The result is cosmic chaos on an unimaginable scale. Galactic harassment is different from a merger. A merger, like the antennae, is when two galaxies collide and stick, becoming one. Harassment is when a galaxy experiences repeated, high-speed encounters with its many neighbors over billions of years. These are not full-on collisions. They are brief, violent, gravitational drive-by interactions that gradually, but relentlessly, tear smaller systems apart. Imagine a small galaxy is a carefully constructed sandcastle on the beach. A merger, like the antennae, is like someone coming along and deliberately stomping on the castle, destroying it in one go. Galactic harassment, however, is like the tide coming in. Each individual wave is small and just brushes the castle. A single wave doesn't destroy it. It just washes away a few grains of sand. But over the course of an hour, the cumulative effect of all those small, relentless waves erodes the castle's structure, washing it away grain by grain until nothing recognizable remains. This is exactly what happens to galaxies in rich clusters. The waves are the powerful tidal forces from massive passing neighbors. The process is particularly devastating for spiral galaxies, like our own Milky Way. Their beautiful, delicate spiral arms and their extended, thin disks of gas are easily disrupted by these tidal forces. During each high-speed harassment encounter, streams of stars get stripped away from the spiral arms and pulled out into space. At the exact same time, the galaxy is suffering from that ram pressure stripping we saw earlier with the jellyfish galaxies. As it plummets at millions of miles per hour through the superheated, 100 million degree gas that fills the cluster, this intergalactic medium acts like a cosmic wind, stripping away all the cold gas needed for future star formation. So, the galaxy is being starved of fuel and dismembered by gravity, all at the same time. The Hubble Space Telescope has captured dramatic images of this harassment in action throughout the Coma Cluster. We see galaxies that are distorted and stretched, with long ghostly tails of stars trailing behind them like cosmic contrails. Some systems are so thoroughly disrupted that they barely resemble galaxies at all, appearing more like shapeless clouds of stars scattered across hundreds of thousands of light years. One of the most striking examples is a galaxy designated NGC 4676, nicknamed the Mice. This system started as two separate spiral galaxies that experienced a close encounter about 160 million years ago. The gravitational interaction stretched both galaxies into long, narrow shapes resembling the tails of mice. But the mice represent just one moment in an ongoing process of destruction. Computer simulations show that these long tidal tails will eventually be stripped away entirely. The stars scattered in those tails will either be ejected into intergalactic space to wander as orphans for eternity, or will eventually fall back to join one of the surviving compact galactic cores. The combined effect of harassment and gas stripping is what transforms the population of galaxies in clusters over cosmic time. This is why, when we look at rich clusters today, they are dominated by large, old, red and dead, elliptical galaxies and small, gas-poor systems called dwarf ellipticals. Very few large, beautiful spiral galaxies can survive in these violent environments. This cosmic violence has been operating for billions of years, fundamentally reshaping the very nature of galaxies throughout the universe. But all of this, the harassment, the mergers, the jellyfish, the cannibals, all of this visible destruction is just the tip of the iceberg. It's all just a shadow play, a grand ballet dictated by an invisible architecture that shapes everything we can see, everything you can see in the universe. Every star, every nebula, every glowing galaxy ... all of it is built on a foundation of something that is, and may forever be, completely invisible. We call it dark matter. It is the great overriding mystery of modern cosmology. It makes up roughly 85% of all matter in existence. And yet, it interacts with virtually nothing, except gravity. It does not emit light. It does not absorb light. It does not reflect light. You, me, and this entire planet are at this very second passing through a constant, diffuse wind of dark matter particles, and we feel absolutely nothing. It is, in every sense, the ghost of the cosmos. But without this invisible scaffolding, none of the galaxies we have just been exploring could possibly exist, with the one baffling exception of NGC 1277, the impossible skeleton we discussed earlier, which remains a profound puzzle. Think of dark matter as the skeleton that gives shape to the cosmic body. Just as your bones provide the rigid framework that allows your muscles and organs to maintain their structure, dark matter provides the gravitational framework that allowed normal matter, the hydrogen and helium gas, to clump together in the first place into stars, galaxies, and larger structures. The gravity of normal matter alone is not strong enough. There would be no structure, no stars, no planets, and no us. How can we be so sure of something we cannot see, touch, or detect? The evidence for dark matter is overwhelming, and it comes from multiple, independent sources. First, there's the rotation of galaxies. When astronomers measure how fast stars are orbiting around the centers of spiral galaxies, like our own, they find something that defies the known laws of physics. The outer stars are moving much too quickly. Based on the gravity of the visible matter, the stars and gas we can see, these stars should be flung off into space, like children falling off a merry-go-round that's spinning too fast. The only way the galaxies can stay intact is if they are embedded in a massive invisible halo of matter that is providing the extra gravitational pull needed to hold them together. Second, there's the behavior of galaxy clusters. This was the original clue. Back in the 1930s, the astronomer Fritz Zwicky was studying the Coma cluster, the same one we just visited. He calculated how fast the individual galaxies were moving and realized they were moving so fast that the cluster as visible gravity was not nearly enough to hold them together. The cluster, he calculated, should have dispersed, flying apart billions of years ago. The only explanation was that the cluster contained far more mass than could be seen, hidden in some invisible form. He was the one who named it Dunkel Mattery, dark matter. Finally, in the modern era, we can literally map it. We use a remarkable technique called gravitational lensing. As Einstein predicted, massive concentrations of matter including dark matter bend and distort the very fabric of spacetime. As light from distant, background galaxies passes through this warped space, it is bent and distorted, creating a cosmic funhouse mirror effect. By measuring this distortion, astronomers can create detailed maps of where the invisible matter is located. These maps show us the grandest structure in the universe, the cosmic web. Dark matter is not clumped randomly. It forms a vast, intricate, beautiful web-like structure that spans billions of light years. This cosmic web consists of great, long filaments of dark matter, and at the intersections of these filaments, in the massive nodes, is where the galaxy clusters, like coma, reside. Between these filaments lie enormous empty voids, where very little matter of any kind exists. This web-like pattern provides the underlying architecture that determined where galaxies would form, and how they would be distributed throughout all of space. On smaller scales, every galaxy, including our own, sits at the center of one of these dark matter halos, which extends far beyond the visible stars. Our own Milky Way, with its 100,000 light-year wide disk of stars, is embedded within a vast dark matter halo that is estimated to stretch at least 600,000 light-years from the galactic center, 3 times larger than the visible galaxy itself. It is the invisible ocean in which our tiny, shining island of light is floating. And yet, as we delve deeper into that strange primordial galaxy, G-SIN-DG 9422, the mystery only intensifies. We've established that the gas is somehow outshining the stars, but the scale of this phenomenon is what is so baffling. In this ancient system, the fundamental relationship between stars and gas has been flipped completely, turned entirely on its head. This profound discovery was a gift from the James Webb Space Telescope. Its powerful infrared spectrograph, an instrument that acts like a cosmic prism, is what allowed us to capture the faint, 13-billion-year-old light from this galaxy and dissect its fingerprint. When the lead researcher, Alex Cameron, first saw the resulting data on his screen, his reaction wasn't one of complex academic jargon, but of pure, unfiltered human astonishment. His simple, immediate assessment: "That's weird." It was, in fact, exactly the kind of totally new phenomenon that the Webb telescope was designed and hoped to find in the deep, early universe. The spectrum, the data from that light, showed the unmistakable signatures of highly ionized gas. This is a scientific term, but what it means is that the atoms in these vast, galaxy-spanning clouds have been violently stripped of most of their electrons. This state of being requires a colossal, overwhelming input of high-energy radiation, far more energy than all the observed stars in that galaxy could ever hope to provide. It truly is, as we've hinted, like finding a massive cauldron of water boiling furiously. But when you look beneath it, you find only a single tiny candle. The energy output simply does not match the energy source. Working with theorist Harley Katz, the team ran sophisticated computer models to try and answer the one burning question: what could possibly create such extreme, unexplained conditions? Their conclusion is as fascinating as the discovery itself. It suggests that G-SIN-DG 9422 is likely home to a different kind of star. Not the familiar stars we see today, but primordial monsters. These are not the stars we know. These are theoretical behemoths, perhaps hundreds of times more massive than our Sun, with surface temperatures themselves exceeding 140 degrees Fahrenheit. These stellar monsters would have lived incredibly brief, violent lives, all the while pumping out unimaginable quantities of high-energy ultraviolet radiation, enough to ionize their entire host galaxy. And this This is where the implications of one weird galaxy become profound, stretching across the entire history of the cosmos. This gas outshining phenomenon might be the long-sought-after missing link in our understanding of how the universe itself evolved from its dark, opaque beginnings into the star-filled cosmos we see today. As we've explored, during the first few 100 million years after the Big Bang, the universe was filled with a thick neutral hydrogen gas. It was a dark age, where this primordial fog blocked most light from traveling very far. Something had to burn off that fog. Something had to ionize all of that hydrogen to make the universe transparent, an event astronomers call the epoch of reionization. It has long been suspected that the very first generation of stars was responsible for this. But there's a persistent problem with that theory. Regular stars, even the massive ones we know today, don't seem capable of producing enough of the right kind of ultraviolet radiation to get the job done. Our models of reionization always come up a bit short. But galaxies like GSND G9422, with their superheated gas and their theoretical monster stars, might be showing us exactly how it happened. These hyper-efficient stars, living fast and dying young, could have been the cosmic blowtorches that finally and rapidly cleared the fog, allowing light to travel freely across the universe for the very first time. But as strange as these hyperluminous primordial galaxies are, the universe, in its infinite variety, also presents us with the perfect haunting opposite. What if there are structures, as massive as our own Milky Way, that harbor no visible light at all? What if there are galaxies that cast a gravitational shadow but emit no glow? Hidden throughout the cosmos, we believe there are dark galaxies. These represent some of the most mysterious and frankly eerie objects in existence. They are not just faint. They are, for all intents and purposes, invisible. They are predicted to have enough mass to qualify as a galaxy, containing perhaps billions of times the mass of our Sunday. But all of that mass is dark matter. They have no stars, no gas, and emit no light across any wavelength of the electromagnetic spectrum. They are, in essence, invisible cities of dark matter, floating silently through the cosmic void, detectable only through the gravitational ripples they create in their wake. Their existence wasn't an accidental discovery, but rather a prediction that emerged from our most advanced computer simulations of cosmic structure. These models, which traced the evolution of dark matter from the Big Bang to the present day, showed that while most dark matter halos should successfully capture enough normal baryonic matter, like hydrogen gas, to form the visible galaxies we know and love, some halos should fail. Perhaps they formed in regions of space where there was very little gas to begin with. Or perhaps some other, more violent process prevented the normal matter from ever falling into them. In either case, the simulation predicted they would remain dark. So, how do you find something that is, by definition, invisible? It requires detective work on a truly cosmic scale. Astronomers cannot look for them, so they must hunt for them. They look for their gravitational fingerprints. The primary method is a technique we've discussed before: gravitational lensing. When a dark galaxy, by pure chance, passes directly between us and a more distant luminous light source, like another galaxy or a quasar, its immense gravity, though invisible, will bend and distort the fabric of spacetime. The light from the background object is warped as it passes, creating telltale distortions, arcs, smears, or multiple images that reveal the presence and mass of the invisible object. One of the most compelling candidates identified so far is a massive, invisible object discovered through just such a lensing effect, located in the direction of the nearby Virgo cluster. The math shows that this thing contains roughly 1 billion times the mass of our Sun. It has the mass of a respectable galaxy. And yet, it produces no detectable light. Not in visible light, not in X-rays, not in radio waves. Nothing. It is a ghost in every sense of the word. This, of course, is the profound mystery. Why? What could possibly prevent such a massive gravitational well from doing what gravity does best, collecting gas and forming stars? Several theories compete for the explanation. One possibility is that these dark galaxies formed in regions where the surrounding intergalactic gas was simply too hot. High-energy radiation from nearby, brighter galaxies, or massive black holes could have heated the gas to such extreme temperatures that its atoms were moving too fast to be gravitationally captured by the dark matter halo. A second theory proposes that dark galaxies are failed galaxies. Perhaps these halos did begin to capture gas and form stars, but some catastrophic, early event like a close encounter with a much larger galaxy violently stripped away all of their normal matter, leaving only the dark matter skeleton behind. The most intriguing, and perhaps unsettling, possibility is that they represent a completely different evolutionary pathway, one that our theories don't yet account for. The James Webb Space Telescope is now shedding new light on this, quite literally. Its incredible sensitivity is allowing it to see galaxies so incredibly faint, ultra-faint dwarf galaxies, that we previously thought they were dark. Some candidates for dark galaxies are turning out to just be very, very dim. And this is the crucial part, of the candidates remain stubbornly, profoundly dark, even to Webb's all-seeing infrared eye. These confirmed dark galaxies challenge our fundamental understanding of the relationship between dark matter and normal matter. They suggest that the process of galaxy formation is far more complex and perhaps more fraught with failure than our current models predict. And what makes this all the more mind-bending is the realization that these ghosts, these dark cities of the cosmos, are not just isolated anomalies. They are components. They are parts of an even larger, vaster, invisible framework that connects every single visible structure in the cosmos. Have you ever thought about your true cosmic address? Most of us, if asked, know our home, planet Earth. We know our neighborhood, the solar system. And we know our city, the Milky Way galaxy. But that's like saying you live in a house without ever mentioning your city, your state, or even your continent. Our house is part of a much, much larger gravitationally bound structure. Your full cosmic address includes the local group, our family of 50-odd galaxies. That local group is a member of the Virgo cluster. And that cluster, along with 100,000 other galaxies, is part of a single, colossal structure, the Laniakea supercluster. What's astonishing is that humanity only learned this, our true cosmic neighborhood, in 2014. Before that, we had no idea where the boundaries of home truly were. The name, given by the team that discovered it, is Laniakea. It is a beautiful Hawaiian name that means immense heaven. It is a fitting poetic description for a structure so vast that light takes over 520 million years to cross from one side to the other. The discovery wasn't made by seeing Laniakea. You can't. It is far too large, its components too spread out, to be seen as a single thing. It was discovered by mapping the motion of galaxies. While the entire universe is expanding, pulling most galaxies away from each other, gravity is a local force that fights back. It creates additional, peculiar motions as galaxies are pulled toward massive concentrations of matter. By meticulously measuring these peculiar velocities for tens of thousands of galaxies, astronomers could, for the first time, trace the gravitational flows. They could map the cosmic rivers and streams. What they found was astounding. The Milky Way, Andromeda, the Virgo cluster, and tens of thousands of other galaxies. All of them are flowing. They are like water in a great cosmic river, all streaming toward a single massive and unseen gravitational basin at the center of Laniakea. This central point is known only as the Great Attractor. It's a region with the mass of tens of thousands of galaxies, and it is pulling our entire cosmic neighborhood toward it at over 1.3 million miles per hour. But the story doesn't end there. In a perfect illustration of the cosmic maxim, there's always a bigger fish, Laniakea itself, This entire half-billion light-year-wide supercluster is also flowing. It is being pulled, as one, toward an even larger structure. Another concentration of mass, known as the Shapley attractor, located roughly 700 million light-years away. This creates a cosmic river of galaxies, all streaming in the same general direction, across distances that dwarf our previous conceptions of large-scale structure. The Virgo cluster, which we once thought was the center of our universe, is now understood to be just a dense, urban center within Laniakea. Our local group, containing the Milky Way and Andromeda, occupies a relatively quiet, sparsely populated region on the absolute outskirts. We are, in effect, living in a cosmic suburb, and we should perhaps be grateful for that. This peaceful, suburban location, far from the violent collisions and harassment happening in the dense clusters, may have been crucial for allowing the delicate, uninterrupted eons needed for complex life to evolve on Earth. The very structure of Laniakea, these flows, these empty spaces, these dense clusters, this is the first time we've been able to truly see the cosmic web in action. Laniakea, our immense heaven, is just one continent. But it is a continent that is connected to a vast global network. The universe, it turns out, is built like a cosmic spiderweb. This is not just a poetic metaphor. It is the fundamental architecture of the cosmos. The vast empty voids are the gaps in the web, and the threads that stretch between them, connecting everything, are the galaxy filaments. These filaments are the largest known structures in the universe. A typical filament, a modest thread in this cosmic tapestry, might be 160 to 260 million light-years long. But some are true cosmic monsters. The largest confirmed structure, a truly colossal assembly of filaments, is known as the Hercules Corona Borealis Great Wall. This structure stretches for a mind-shattering, almost incomprehensible 10 billion light-years across space. Let that number sink in. That is roughly 1/10 the diameter of our entire observable universe. If you could somehow travel at the speed of light, it would take you 10 billion years, just to cross it. These filaments form the absolute backbone of cosmic architecture. They connect the massive galaxy clusters and superclusters, like Laniakea, in a vast, three-dimensional web that spans the entire universe. The pattern is hauntingly familiar. It resembles a biological neural network or the intricate internal structure of a living cell. And where did this grand, web-like structure come from? It emerged from tiny, microscopic, quantum-scale fluctuations in density that existed just a fraction of a second after the Big Bang. During the period of cosmic inflation, these microscopic variations were stretched to astronomical scales. Over the next 13.8 billion years, gravity, the universe's great sculptor, amplified these tiny differences. And as always, dark matter led this cosmic construction project. Because it only interacts with gravity, it could begin clumping together long before normal matter could. It formed the invisible scaffolding, the vast web-like skeleton. Normal matter, the hydrogen and helium gas, was then pulled by gravity into these pathways of least resistance. It followed the dark matter's gravitational lead, flowing along these filaments to create the galaxies we observe today. The space within these filaments, the space between the galaxies, isn't empty. It's filled with a tenuous, diffuse gas known as the warm-hot intergalactic medium, or WA. And here is a truly stunning fact. This thin, invisible gas, spread across these vast volumes, contains more normal matter than all the stars in all the galaxies combined. The stars, the brilliant points of light we see, the things we call the universe, they are just the foam on the ocean. The real ocean is this dark, warm, invisible gas flowing along the filaments of the cosmic web. Detecting these filaments is, again, an act of cosmic detective work. The gas is too thin to glow brightly, and the dark matter is invisible. Astronomers find them by patiently mapping the locations of thousands of galaxies, and by using gravitational lensing to detect the web's subtle bending of light. The cosmic web is not just a passive structure. It is the engine of galactic evolution. It profoundly influences how galaxies live and die. Galaxies located within a filament are like cities on a major river. They have access to a steady, inflowing supply of fresh, cool gas, which flows along the dark matter streams. This cosmic buffet fuels ongoing star formation, allowing these galaxies to remain active and continue growing for billions of years. Conversely, galaxies that end up in the vast, empty spaces between the filaments, the voids, are cut off from this supply. They are starved. They quickly exhaust their internal gas supplies and fade into old, red, and dying systems. The cosmic web, quite literally, determines which galaxies thrive and which ones wither away. This cosmic web also creates structures so mind-breakingly large that, according to our most fundamental theories, they shouldn't exist. These are the Great Walls. The Sloan Great Wall, discovered in 2003, is one such structure. It is a vast, sheet-like arrangement of galaxies and filaments that stretches for over 1.3 billion light-years. But even it pales in comparison to the previously mentioned Hercules Corona Borealis Great Wall. This cosmic behemoth, at 10 billion light-years across, is so large that some astronomers question if it can actually exist as a single connected structure within our current cosmological models. These great walls represent the largest density enhancements in the cosmic web. They are regions where multiple galaxy filaments converge, creating vast, sheet-like structures that contain millions of galaxies. They form the boundaries between the vast cosmic voids, like the shimmering, iridescent walls of enormous soap bubbles floating in space. Their discovery and their sheer scale came as a profound shock to cosmologists. Why? Because they approach, and perhaps exceed, the theoretical maximum size that any structure in the universe should be able to reach. This rule is called the cosmological principle. It is one of the fundamental, bedrock assumptions of all modern cosmology. It states that on the largest scales, the universe should be homogeneous and isotropic, a fancy way of saying it should be roughly the same everywhere, with matter distributed uniformly, like butter, spread evenly on toast. Structures like the Hercules Corona Borealis Great Wall test the absolute limits of this assumption. The problem, as with so many of these cosmic mysteries, is time. Gravity builds structure, but gravity is limited by the speed of light. No gravitational influence can travel faster than light. The universe is only 13.8 billion years old. That means there simply should not have been enough time since the Big Bang for gravity to coordinate the formation of a single, coherent structure that is 10 billion light-years across. And yet, these cosmic walls clearly exist. This forces astronomers to reconsider some of their most basic assumptions. Perhaps the early universe, in its very first moments, contained much stronger, larger seeds for structure than our current theories of inflation predict. Or perhaps there was some form of exotic physics during cosmic inflation that created preferred directions in space, leading to enhanced structure formation along these specific massive axes. The existence of these walls also, in a strange way, gives us crucial insights into dark energy, the mysterious force that is accelerating the expansion of the universe. The very fact that these large structures could form at all places hard limits on how strong dark energy could have been in the past. Too much dark energy, too early, would have pushed everything apart and prevented the formation of these great walls entirely. These walls aren't solid barriers, of course. They are enhanced regions of the web, containing billions of galaxies, all organized into smaller groups and clusters, which are in turn connected by filaments. It's a fractal pattern where each level of magnification reveals a similar, beautiful organizational structure. But for every wall, there is a space. For every thread of the web, there is an emptiness. Between the massive filaments and the great walls lie the cosmic voids. These are not just empty space in the way we normally think of it. These are regions so profoundly, so incomprehensibly empty that they make the vacuum of interplanetary space look crowded by comparison. They are the largest empty spaces in the universe, commonly spanning hundreds of millions of light years. The most famous of these is the Boat's Void, often called, with chilling accuracy, the Great Nothing. Discovered in 1981, it is a roughly spherical region of space, about 330 million light-years in diameter, that is almost completely devoid of galaxies. We expected to find thousands of galaxies in a region this large. We found a few dozen. The emptiness is so profound that it leads to a powerful what-if scenario. Have you ever considered how lucky we are to live where we do, in a suburb of a major galactic city? If our own Milky Way galaxy had, by chance, formed in the center of the Boat's Void, we would live in a universe of unimaginable loneliness. The night sky would be almost perfectly black. We wouldn't have discovered that other galaxies even existed until the 1960s, with the advent of our most powerful telescopes. Even today, we would know of fewer than a dozen of them, faint smudges on the edge of our perception. Our entire conception of the cosmos, our mythology, our science, would be fundamentally different. It's important to understand how these voids formed. They didn't form from some cosmic explosion that cleared out the matter. They are not holes. They are, instead, regions where the initial density of matter, just after the Big Bang, was just slightly lower than average. Gravity is a rich-get-richer system. Over billions of years, the denser regions, which would become the filaments and clusters, had more gravity, so they pulled in matter from their surroundings. This meant that the underdense regions became, well, even emptier. Their sparse matter was gravitationally pulled out of them, flowing toward the denser regions, leaving these vast voids behind. And this process is still continuing. The voids are gradually expanding, merging, and becoming even emptier over cosmic time. And yet, they are not perfectly empty. The few galaxies that do exist inside them, the void galaxies, are fascinatingly strange. They tend to be small, blue, and actively forming stars. This, of course, is another puzzle. In such isolated environments, they should have exhausted their internal gas supplies billions of years ago. One leading explanation is that this very isolation protects them. They are never subjected to the galactic harassment, the ram pressure stripping, or the violent mergers that plague galaxies in the urban cluster environments. They are free to live long, quiet, and slow lives. For scientists, these voids are crucial. Because they contain so little matter, their evolution is dominated almost entirely by the expansion of space itself. They are perfect natural laboratories for studying the effects of dark energy, emptiness and structure, light and dark. These are the dueling forces of our cosmos. And even these vast empty regions exist within a universe where matter and energy are locked in a constant spectacular state of warfare. The final stage of structure formation is not a quiet process. It is the most violent thing the universe can produce. Right now, 5.4 billion light-years away, 4 massive galaxy clusters are all colliding at the same time in the most violent, energetic event our universe has witnessed since the Big Bang itself. The collision is happening in a region of space known as Max J 0717. Each of these 4 clusters contains hundreds of galaxies, trillions of stars, and quadrillions of tons of hot gas and dark matter. When objects this massive collide at speeds of thousands of miles per second, they unleash more energy than the simultaneous explosion of billions of supernovae. This is the ultimate expression of gravitational violence. The Chandra X-ray Observatory, which sees the universe in high-energy X-rays, has captured stunning images of this cosmic pileup. It doesn't see the stars or the galaxies. It sees the hot gas, which glows at temperatures of over 100 million degrees Fahrenheit. As these 4 clusters merge, their vast clouds of intergalactic gas slam into each other, creating colossal shock waves, cosmic tsunamis, that propagate outward for millions of light years, heating the material to even more extreme temperatures. But perhaps the most fascinating aspect of this immense violence for science is how it acts as a cosmic filter. It is a natural experiment that separates the different types of matter. The hot gas in each cluster, which we see in X-rays, behaves like a fluid. It experiences friction and ram pressure. When the clusters collide, this gas slams into the other gas clouds, slows down, and lags behind. The galaxies themselves, however, are so dense and compact, and mostly empty space, that they are like bullets. They feel very little friction. They pass through each other like ghosts, continuing to sail ahead. And the dark matter? It behaves just like the galaxies. It feels only gravity. It doesn't interact with the gas or itself. It, too, passes right through the collision, sailing ahead with the galaxies. This creates a spectacular and deeply informative situation. The galaxies and the dark matter, the bullets, sail ahead, while their own gas, the smoke, is left behind, smeared out in the middle of the collision. The most famous textbook example of this is the bullet cluster. That two-cluster collision provided some of the strongest independent evidence for the existence of dark matter. Why? Because gravitational lensing showed that most of the mass ... the gravity ... was with the bullets, the galaxies, not with the smoke, the hot gas, which is where most of the normal matter was. The violence of these cluster collisions also triggers new life. The shock waves that rip through the merging clusters compress smaller gas clouds within the galaxies themselves, igniting intense, furious bursts of star formation. These grand cosmic battles, these pileups of hundreds of galaxies, and their dark matter halo, represent the final, culminating stage of structure formation in our universe. They are the last act of gravity, building the largest, most massive, and most violent objects the cosmos will ever know. And so, those colossal, universe-altering battles, the great cluster collisions we just witnessed, they are themselves, in a very real sense, living on borrowed time. They represent the final, magnificent, flaring embers of a dying age, the age of structure. This is because the other, greater, and far more mysterious power in the universe, that invisible, relentless force we call dark energy, is winning its cosmic tug-of-war. It is accelerating the expansion of space itself. The cosmic web, that grand architecture of filaments and walls, is being stretched. The superclusters, our continents of light, are being driven apart faster and faster. In the unimaginably distant future, this means that galaxy clusters will become increasingly, and then permanently, isolated from one another. The era of major cluster collisions, the most violent and energetic events since the dawn of time, will eventually come to a cold, quiet end. The universe will settle into a state of profound, eternal loneliness, a cosmos of isolated island galaxies, separated by an ever-expanding, uncrossable ocean of void. But the violence of those collisions is just one part of a much larger, and mostly invisible, cosmic ecosystem. It's an ecosystem where matter flows between these great structures in ways that were completely hidden from our view until very, very recently. We now know that between every galaxy, in the vast, dark spaces that fill the filaments of the cosmic web, there flows a cosmic river. This is not a river of water, but of a diffuse, ethereal gas, heated to temperatures that make the surface of our sun seem cool by comparison. This is the intergalactic medium, or IGM. It is a plasma, a roiling sea of matter so hot often exceeding 10 million degrees Fahrenheit that the atoms themselves have been torn apart. They have been completely stripped of their electrons, and now exist only as bare nuclei, swimming in a roiling sea of free, high-energy particles. This material is so astonishingly tenuous, so thin, that any cubic meter of it here on Earth would be classified as a perfect hard vacuum. And yet, Here is one of the most staggering facts in all of cosmology. There is so much of this empty space that this invisible superheated plasma, this river, contains more normal matter than all the stars in all the galaxies combined. Let that settle in for a moment. Everything we see, every star that glitters, every nebula that glows, all of it is just the foam on the ocean. The real ocean of normal baryonic matter is this invisible superheated fog. These cosmic rivers are not random. They precisely follow the invisible scaffolding of the dark matter filaments that connect the great galaxy clusters. They create a vast cosmic circulatory system, transporting matter and energy across billions of light years. Gas flows along these channels like blood through cosmic arteries, carrying the raw, primordial materials needed for galaxy formation from one structure to another. But why is this gas so impossibly hot? Its temperature, which seems to defy the coldness of space, has two primary origins. Gravitational heating. The first is the simple, violent act of formation. As matter falls into the deep gravitational wells of the dark matter filaments, it gets compressed and heated, the exact same principle as air getting hot when you pump up a bicycle tire, but scaled up to cosmic proportions where gravitational heating can raise temperatures to millions of degrees. Cosmic feedback. The second source is from within the galaxies themselves. Countless supernova explosions, the death cries of massive stars, blast superheated gas and heavy elements out of their host galaxies at speeds of thousands of miles per second. This feedback material, enriched with the carbon, oxygen, and iron forged in stellar cores, joins the intergalactic flow. It is then carried along the cosmic web, where it can eventually be recycled, cooling and falling into new generations of galaxies. This intergalactic medium is, as you might guess, largely invisible to optical telescopes. Hot plasma simply doesn't emit much light in the visible wavelengths our eyes can see. Instead, astronomers must hunt for it using specialized tools. X-ray telescopes, like the Chandra Observatory, can see the high-energy radiation, the X-ray glow, that is produced as this plasma swirls through the intense magnetic fields generated by galaxy clusters. More recently, observations from the Planck satellite have mapped some of these connections by detecting something called the thermal Sunyaev-Zeldovich effect. This is a subtle process where the photons of the cosmic microwave background, the Big Bang's afterglow, pass through this hot plasma and get kicked, boosting them to slightly higher energies in a way that we can measure. But the most dramatic, and perhaps most elegant, discovery came from a completely unexpected source. It came from mysterious, fleeting flashes of light from the other side of the universe. For decades, astronomers were faced with a profound, embarrassing, and fundamental mystery. They called it the missing baryon problem. It was a detective story. The crime was a cosmic budget that simply didn't add up. From our precise measurements of the cosmic microwave background, the afterglow of the Big Bang, we know exactly how much normal matter, or baryonic matter, the stuff made of protons, neutrons, and electrons, just like you, was created in the first few minutes of cosmic history. The models were precise. The physics was sound. We knew, with certainty, that this normal matter should make up about 5% of the universe's total mass energy. But when astronomers tried to find it, they couldn't. They pointed their telescopes at the heavens and began to count. They counted all the stars in all the galaxies. They counted all the cool gas and dust clouds. They counted the planets, the asteroids, and everything else they could possibly observe. And when they tallied it all up, they came up short. Way short. They could only account for about half of the normal matter that absolutely had to exist. This wasn't dark matter, which is its own separate mystery. This was the ordinary, everyday matter that we are made of. Half of it had, seemingly, vanished from the cosmic census. Where did it go? For decades, this question haunted cosmology. The missing baryons were hiding somewhere, but despite searching with increasingly powerful telescopes, roughly half of all normal matter remained missing. The solution, the smoking gun, came from fast radio bursts, FRBs. These are brief, spectacularly powerful flashes of radio waves from distant, far-off galaxies. They last for just a few milliseconds, but in that flicker, they can release more energy than our sun produces in an entire day. These cosmic beacons, these celestial lighthouses, turned out to be the perfect tools for detecting the invisible intergalactic fog. They were the key that unlocked the entire mystery. Here is how. When a signal from an FRB, a packet of radio waves, travels billions of light years to reach us, it must pass through all of that missing hot plasma in the intergalactic medium. As it does, it interacts with all the free electrons in that plasma. This interaction has a very specific, measurable effect. It causes the longer radio wavelengths to be delayed, arriving at Earth just a tiny, tiny fraction of a second later than the shorter wavelengths. It's like a cosmic race where one runner has to wade through a thicker medium, slowing it down just a bit. By studying this dispersion delay from hundreds of FRBs and knowing the distances to their host galaxies, astronomers could, for the first time, calculate the total number of electrons the signal had to encounter during its entire journey. The results solved the missing baryon mystery definitively and completely. The lost matter was found. It had been hiding in plain sight all along, spread throughout the vast, tenuous superheated filaments of the cosmic web. This warm, hot intergalactic medium, so thin that it's nearly nothing, is so vast that it accounts for the entire missing half of the universe's normal matter. This discovery was a triumph of 21st century astronomy. It fundamentally changed our understanding of how matter is distributed, creating a complete budget for the first time. Half of all normal matter, 2.5% of the universe, is in stars, galaxies, planets, etc. The other half, 2.5% of the universe, is in this hot, diffuse intergalactic medium. The other 95% remains the profound mystery of dark matter and dark energy. This finding has profound implications. This IGM serves as the great reservoir, the gas tank that galaxies can, in theory, tap into for future star formation. But it's also heated to such extreme temperatures that it's very difficult for a galaxy's gravity to capture it. This creates a delicate cosmic thermostat, regulating how quickly and if galaxies can grow over time. But how do we know this? How do we map this cosmic tapestry? How do we see the evolution of these galaxies from the cosmic dawn to the present day? The answer lies in a story of scientific audacity. In what appears to be the single emptiest, darkest, most uninteresting patch of sky imaginable, the Hubble Space Telescope found 10,000 entire galaxies hiding in the darkness. The story of the Hubble Ultra Deep Field, HUDF, is now a legend. It required astronomers to commit to an observation that at the time seemed almost recklessly wasteful. They decided to point the most powerful and expensive observatory humanity had ever built at T-nothing. They chose a tiny region of sky in the constellation Fornax. It was a patch of utter blackness, chosen specifically because it had no bright nearby stars in it. This patch of darkness was impossibly small. If you held a single grain of sand at arm's length, that grain would completely cover the entire observation field. And yet, Hubble stared. It stared at that tiny, empty speck for over 11 days. It collected 800 separate exposures, patiently gathering photon by photon, building an image from a darkness deeper than we had ever probed. What emerged from those 11 days of patient observation didn't just change our understanding of the universe. It shattered our sense of scale forever. That empty patch of sky was not empty. It was filled. It revealed 10,000 galaxies, scattered like cosmic jewels of every shape, every color, and every age. Nearly every single point of light in the resulting image is not a star, but an entire galaxy, a city of billions of stars, billions of planets, and billions of years of history. The image is a profound cosmic time machine. Because light travels at a finite speed, we are looking at galaxies at different distances, which means we are seeing them at different epochs in cosmic history. The large, bright, well-formed spirals in the foreground are the nearby galaxies, seen as they were perhaps a few billion years ago. The faint, red, and chaotic-looking smudges in the background are the true treasures. They are the primordial systems, seen as they were when the universe was less than 1 billion years old. It's like viewing a single family photograph that spans 13 billion years of cosmic evolution. We see galaxy formation in its infancy, small, irregular, blue cosmic pioneers packed with young stars. We see cosmic teenagers, more mature systems. And we see the adults, the elegant spiral and elliptical shapes that we recognize today. The image even captures galaxies in the very act of merging, showing us the cosmic violence that has shaped this evolution. But perhaps the most profound revelation of the ultra-deep field is what it tells us about cosmic real estate. Remember, this tiny patch, with its 10,000 galaxies, represents just 1/13 millionth of the entire sky. If you multiply that, if you assume every similar patch of empty sky is just as crowded ... the total number of galaxies in our observable universe reaches into the trillions. The James Webb Space Telescope, Hubble's successor, has now surpassed even this. With its powerful infrared vision, it is peering past the galaxies Hubble saw, detecting light that is completely invisible to our eyes. It is pushing this cosmic frontier back to just 280 million years after the Big Bang, finding the very first, most ancient galaxies to ever light up the cosmic darkness. But this journey has a limit. As we push our telescopes deeper and deeper, looking further and further back in time, we are inevitably approaching a wall. There is an absolute boundary in space-time beyond which we can never see. This cosmic horizon isn't a physical barrier. It's not a mysterious force field blocking our view. It is a fundamental limit imposed by the universe itself. It exists for one simple reason. The universe hasn't existed long enough for any light from beyond that point to have had time to reach us. At the very edge of our observable universe, at the surface of this horizon, lies the cosmic microwave background, CMB. This is it. This is the wall. It is the afterglow of the Big Bang itself. It is the oldest light in the universe. The CMB represents the flash of light from the moment the universe first became transparent. It was emitted roughly 380,000 years after the Big Bang. Before this moment, an event called recombination, the entire universe was filled with a hot, dense, and completely opaque plasma. It was a fog of free electrons and protons, and light photons, which are light particles, couldn't travel. They would be emitted, but would immediately crash into a free electron, being scattered instantly. Space was completely opaque, like living inside the core of a star. But as the universe expanded, it cooled. And at 380,000 years, it finally became cool enough for those electrons and protons to recombine and form the first stable, neutral hydrogen atoms. When this happened, the fog cleared instantly. All the photons that were trapped in the plasma were suddenly set free, and they began to travel through space, unscattered, for the very first time. The cosmic microwave background is that flash of liberation. It is the first light that was ever free to travel, and it has been traveling across the expanding universe for 13.8 billion years, until it finally hits our telescopes today. Here is the crucial point. We cannot see anything that happened before this moment. No light from earlier times, from the universe's first 380,000 years, can reach us because the universe itself was opaque. This forms a fundamental wall to our observations. Behind this wall lie the cosmic dark ages, the era when the first stars were just beginning to form, their light struggling to propagate through the neutral hydrogen fog. This brings us to one last, mind-bending piece of cosmic geometry. The universe is 13.8 billion years old. We are seeing light from the CMB that has traveled for 13.8 billion years. So, you would be forgiven for thinking that the edge of our observable universe is 13.8 billion light-years away. It is not. The observable universe extends roughly 46.5 billion light-years in all directions from Earth, giving it a total diameter of about 93 billion light-years. How is this possible? How can we see something 46.5 billion light-years away if the light has only had 13.8 billion years to travel? The answer is the one constant, complicating factor in all of cosmology: the expansion of space. Think of it like this. A photon of light is like a runner on a cosmic treadmill. The photon began its journey when the galaxy it came from was much closer to us. But in the 13.8 billion years that the photon was running toward us, the treadmill of space itself was expanding, carrying that distant galaxy away from us. By the time we finally receive that photon today, the galaxy that emitted it is now, in the present, a staggering 46.5 billion light-years away. This expansion also leads to a truly strange paradox. Some of the distant galaxies we can currently observe in the sky are now beyond our future light horizon. We can see their ancient light, the light that left them billions of years ago. But the light they are emitting today, will never, ever reach us. The space between us is now expanding faster than the speed of light itself, carrying them away from us forever. The CMB, that wall at the edge of our view, provides us with a baby picture of the universe. And in that picture, we see tiny, microscopic fluctuations in temperature. These are the seeds, the quantum variations from the first fraction of a second, which gravity would later grow into the galaxies, the clusters, and the entire cosmic web we observe today. But the CMB, our baby picture, also tantalizes us. It whispers of what might lie beyond that observational reach. The fluctuations we observe are just the ones that were small enough to fit inside our observable bubble. Much larger, longer variations almost certainly exist beyond our cosmic horizon. And this raises the most profound and perhaps unanswerable questions about the nature of reality itself. Outside the boundaries of everything we can ever observe, beyond that 93 billion light-year bubble, lies an infinite mystery. It is a mystery that dwarfs our observable universe beyond all comprehension. Our best theories, the ones that perfectly describe our local universe, have a staggering logical consequence. If the universe is, as it appears to be, geometrically flat, then it is most likely infinite in extent. Our entire observable universe, all 2 trillion galaxies, all 13.8 billion years of history, all of it, would be just one infinitesimal, finite bubble within an infinite, eternal ocean of space. An ocean containing infinite galaxies, infinite stars, and infinite copies of everything. This is not science fiction speculation. It is the cold, logical consequence of combining finite physics with infinite space. In an infinite universe, every possible arrangement of atoms must occur somewhere, and not just once, but infinitely many times. The mathematics is staggering. In a volume of space roughly 10 to the dash power dash of dash 10 dash, the dash power dash of dash 118 meters across, every possible quantum state, every possible way atoms can be arranged, would be exhausted. This would force an exact repetition. What does that mean in human terms? It means that somewhere out there, far, far beyond our cosmic horizon, in a galaxy you will never see, there is another planet identical to Earth. And on it, there is another version of you, reading these exact words, having this exact thought, at this exact moment. But infinity contains more than just identical copies. It contains every possible variation. There are, in this infinite space, versions of Earth where the dinosaurs never went extinct. There are versions of you that made every different life choice you've ever contemplated. There are entire histories that unfolded along completely different timelines, all playing out right now in distant, inaccessible regions of this infinite cosmos. The multiverse concept is just one extension of this. Cosmic inflation theory, our best idea for the Big Bang, suggests that our entire universe, our bubble, might be just one of many, perhaps infinite, bubbles in a grander multiverse. Other bubbles could have different physical constants, different laws of physics. They might be sterile, or they might be home to forms of complexity and consciousness we cannot even begin to imagine. We are finite beings, trying to grasp the implications of infinity. We are limited observers, attempting to understand an unlimited reality. And so, here we are. After a journey that has taken us across 13.8 billion years of cosmic history, after flying past 2 trillion galaxies, from the cosmic dawn to the great cluster collisions of today, we return. We return to Earth. We return to this room. We return to ourselves and to the most profound, most human question of all. What does this all mean? What does it mean for us? Every galaxy we've explored, from the most distant, primordial infant to the massive, cannibalistic giants of the present, was formed from the same fundamental processes that created our own Milky Way. The carbon in your body, the atoms that make up your bones and your brain, was forged in the nuclear furnaces of massive stars that lived and died billions of years ago. The oxygen you are breathing right now came from their death throes, seeding space with the elements of life. You are, in the most literal sense, made of star stuff. You are a child of the cosmos. But this grand cosmic perspective reveals a profound and beautiful paradox. It is a paradox that, I believe, defines the human condition in the 21st century. First, the insignificance. We have learned that Earth is not the center. It is an ordinary planet, orbiting an ordinary star, tucked away in the outer suburbs of a typical galaxy. That galaxy is just one of 50 in a modest group, which is on the outer edge of a vast supercluster, which is itself just one node in a cosmic web that may stretch to infinity. From this perspective, every human conflict, every national boundary, every war fought over a tiny patch of land on this single planet, it all seems almost absurdly small. The rise and fall of our civilizations is a brief, momentary flicker in a cosmic timeline that stretches for billions of years. Second, the preciousness. And yet, in a universe that is overwhelmingly dominated by cold radiation, by hot plasma, by dark matter, and by the violent, sterile extremes of stars, planets capable of supporting the delicate, complex chemistry required for life are, we must conclude, extraordinarily rare cosmic treasures. Earth represents billions of years of cosmic evolution, concentrated and culminating in a single, small, blue world. A world where the universe became conscious of itself. We are, as far as we know, the universe's way of knowing itself. Through human consciousness, the cosmos has developed the ability to contemplate its own existence, to trace its own history, from the first quantum fluctuations to the formation of 2 trillion galaxies. Every telescope we build, every scientific discovery we make, every moment you spend in quiet cosmic wonder, it is the universe looking at itself through your eyes. This realization, this cosmic perspective, carries with it a profound, unspoken responsibility. We are the only known beings capable of understanding, preserving, and transmitting this cosmic knowledge. The story of the universe, in all its grandeur, violence, and beauty, exists in its full, coherent glory only within our collective human consciousness. Our journey through every galaxy reveals that we are living in an age of unprecedented discovery. Never before has our species been able to see so far, to understand so much. And perhaps the most important lesson from it all is that the universe is, and always will be, far stranger, more beautiful, and more awe-inspiring than we ever dared to imagine. We end, then, where we began. We are temporary arrangements of atoms in an infinite cosmos. But we leave with the knowledge that we are participants in the most extraordinary story ever told. We are small, we are temporary, and we are isolated in space and time. But we are also the universe's greatest known achievement. We are matter, organized in such a way that it can finally understand